So now let us continue with the second method, which is used for estimating or calculating the average rainfall over an area. So this method is the one called Thiessen Polygon Method. So you understand that is just the Thiessen. This is the name of someone maybe who was involved in this method, and polygon is just presence of polygons. We see method, Thiessen Polygon Method. The method is also called the weighted mean method. The weighted mean method. That is another name which is given to this method, weighted mean method, or it is also called the nearest neighbor method. So the method, you can call it the Thiessen Polygon method, or you can call it just the weighted mean method, or you can call it just the nearest neighbor method. How does this method work? Mainly this method, they consider that if you have a catchment and you have, let's say, maybe 4 rain gauges, assume that you have 4 stations. Assume that we have 4 stations or rain gauges. You have 4 rain gauges. So the method assumes that if this station 1, 2, 3, 4, these are 4 stations, it assumes that each station, it measures a given rainfall depth. That rainfall depth represents a given area. Each station records a rainfall which represents a given area. Normally, let's say halfway to the next station. So assume that we have a station A. Assume that the nearest station is B. This method, the Thiessen Polygon method, assume that the rainfall recorded by this station is uniform halfway to the next station. If we have, to better understand, if we have like we have like 2 stations, only we have A and B. So we are assuming that this method assumes that the first station records a rainfall which is somehow the same halfway to the next station, meaning that this point here has the same rainfall as the one recorded here. This rainfall is the same as the one recorded here. This rainfall is the same as the one recorded here, and so on, halfway. So if you have a distance like this, if you have this distance is like 5 meters, and here it is maybe 5 meters, the method assumes that the rainfall recorded in this half by this station is the same. So each station or each rain gauge represents a given area halfway to the next rain gauge, meaning that this station B also, the rainfall recorded here is the same as in this point. All these points halfway to the next station received the same rainfall. Mainly this is how this method works. It considers that the points halfway to the next station receive the same rainfall as the one recorded here. If this station has recorded, let's say, 10 millimeter, it means that halfway this point has received 10 millimeters of rainfall. This point has received 10 millimeters of rainfall. This point has received 10 millimeters of rainfall, and so on. This point has received 10 millimeters of rainfall, and so on. and the same if this station has recorded, let's say, 8 millimeters. It means all points halfway to the next station has received the same amount of rainfall, meaning that here it is 8 millimeters, here it is 8 millimeters, here it is 8 millimeters, and so on. So this is how this method works. So it considers the areas represented by each station. And it uses polygons. You see, we are now starting to have polygons. The Thiessen Polygon Method, the polygon. So each station, the rainfall recorded by each station is multiplied by its area. That's how the method works. To better understand the method, we use an example as well. But this method is suitable in which conditions? First of all, we can say that the method is suitable when we have just area of moderate size. So it is better if you use this method in areas of moderate size, not too small or the big sizes. Mainly it is suitable when you have moderate size. And the other thing that we can consider in this method, the method mainly it is suitable when you have maybe few stations, rainfall station, compared to the size of a basin. If you have, let's say, a bigger basin and you have only 3 only stations in the whole basin, so this method is suitable when you have a few weather stations or you have a few rain gauges compared to the size of the basin. This method is also suitable. And the other thing to remember, the third, this method mainly is not suitable for mountainous region due to orographic influence of rainfall. You know, the topography. If you remember the types of rainfall, we have seen that some rainfall are depending on the topography, the one we call the orographic rainfall or orographic precipitation. So in the case of mountainous regions, when we have an area of mountains, this method might be not suitable to apply in that situation. So mainly this is how we can explain it, and this method is suitable or is more accurate compared to arithmetic mean method. Mainly this method is suitable compared to the first one we have seen. So let us now continue with the next point. So mainly to use this method, the Thiessen Polygon Method, if you want to use it to calculate the average rainfall of a given area, there are steps which you have to go through or to undertake in order just to calculate accurately the average rainfall. So these are the steps are shown here. There are 5 steps. The first step, if you want to calculate the average rainfall using the Thiessen Polygon Method, this is the method, the name of the method. Remember that we have called it also the weighted mean method or the nearest neighbor method. So you can call whatever name, but it is mostly known, commonly known as Thiessen Polygon Method. So these are steps you have to go through when you want to compute the average rainfall using the Thiessen Polygon Method. The first one, what you have to do, you have to draw lines joining adjacent or nearby rain gauge. So you have to draw a line. So you draw a line, a straight line joining the 2 stations. Assume that we have, let's say that here we have 2 stations or 2 rain gauges. We have 2 stations, station A and the station B. Assume that this one has recorded 10 millimeters, and this one was recorded maybe 12 millimeters. So we are wondering how we can compute the average rainfall in this catchment using these methods. So what they are telling us, the first step is to draw lines joining adjacent or near rain gauge. Here we have just 2 stations or 2 rain gauges. So trying to draw a line joining the 2 stations, a straight line. We don't have a ruler, but we will try. So here, this is a line which joins the 2 stations, the straight line. Here we are done with this. The next is just a step. What is the next step? Step number 2. So what you will do is just to draw a perpendicular bisector to the lines created in step A. So the first thing we did just is to draw a straight line joining the 2 stations. The next step is just to draw a bisector. Bisector is what is just a line which divides. Of course, it has to be perpendicular to this line, and it divides the region we have, or the line we have, into 2 portions, equal into 2 portions. Meaning that if we have a line like this in the middle, let's say that the middle is, let's say maybe it is this. Yeah, so if it is just maybe, let's say if it is 4 centimeters, you take 2 centimeters and 2 centimeters. This is an example. If you have a 4 centimeters, this is 2 centimeters, the half bisector. So you draw what we call a bisector. So meaning what? This is the half bisector. We do this. This is the bisector. This is the bisector. This is called bisector. So this is a bisector, a line dividing the line that we had before into 2 parts. So which means this part is equal to this. So now we have our bisector. This is the second step. What is next? So maybe we can do this. This is the bisector. So what is the next point? Extend the lines created in step B. The line created, this is the bisector, in both directions to form the representative areas for gauges. Meaning that you have to extend this line to form area which represented by each rain gauge. What is next? Compute the representative area of each rain gauge, which means this rain gauge represents this area. Meaning that each point in this portion is receiving the same amount. Meaning that at this point the rainfall is 10 millimeters. At this point it is 10 millimeters, 10 millimeters, 10 millimeters, 10 millimeters, and so on. At each point we have 10 millimeters. So, and what is next? We need just to find out this area. So you see this is an irregular shape. To find this area, if you want to find this area, you can use an instrument called planimeter. This is a device which can help you just to find out compute area. So it helps just to compute area of irregular shapes. If you have any irregular shapes like this, you can use the instruments to find out this area. Right now we don't have it, but the way you do it, just you go across just the line and it computes the area. So you can get this area. So the other method you can use grids. If you use grids, you can also just find out just the grids. You can use this or use grids. Grids are just whereby you cut your area into a small portion of known size. The grids, if you have the grids, you have like this. These are grids, so you can use planimeter grids. Assume that this area assume that it is maybe area 1 is equal, maybe let's say it has maybe 5 meter or 5 kilometer squared. That is 1. So we have our area and we have our rainfall depth. This is PA. PA is equal to 10 millimeters. So, and let's do the same in this way, in this portion of B, meaning that we have also this area. Meaning what? Each point located in this portion has the same rainfall of 12 millimeters, which was recorded at station B. So mainly this is how we can say. So to find out this area, how big or what is the size of this area, we can also use the parameter or grids. Assume that using the parameter we have gone along these lines and found this area to be equal to, let's say area 2 is equal to, let's say 8 kilometer squared. That is an example. So we have area of each portion, and we have the rainfall recorded at each station. So assume that this is PB. PB is equal to this. So what is the last station? I mean, what is the last point or the last step? So once you have your area, you have your areas. Once you have computed the areas, what is next? You do what? You compute the aerial average rainfall or precipitation using this formula. Meaning what? So what you do, just you do the summation of these products, area of each portion times the precipitation recorded in that portion plus the next product and so on, all divided by the total area of the basin or of the catchment. In this example, in our example, you see that we have only 2 stations, meaning that the precipitation, the average precipitation in our example is equal to area 1, this one, times the first precipitation, if you call it maybe pH, or if you want, you can maybe call precipitation 1, precipitation 2, precipitation 2. If you want area 1 times the precipitation measured here plus area 2 of this portion times the precipitation recorded at this point, 2, over the total area, over area 1 plus area 2. Mainly this is the total area. So if we replace just the values, we get what? Precipitation average will be equal to area 1, 5 kilometers, meter squared, times just the precipitation, times the precipitation 1, precipitation recorded here is 10 millimeters, plus what? Area 2, which is 8 kilometers, times what? The precipitation 2, let's say 12 millimeters, over what? Over the summation of areas, we have 5 kilometer square plus 8 kilometer squared. What will be the precipitation, average precipitation? So let us compute. 5 times 10, this is 50. This is 50 kilometer squared millimeter plus what? 12 times 8, which is 96 kilometer squared millimeter over what? This is 13 kilometer squared, making what? So here we have 96 plus 50. This is the 146 kilometer square millimeter over 13 kilometer squared. So they cancel each other, the kilometers, then we remain with what? The average precipitation will be equal to what? 146 divided by 13. We remain with 11.2 millimeter. So mainly this is the average precipitation in this catchment. This is how we compute the average precipitation using Thiessen Polygon Method. So this is an example where we had 2 stations. Let us see now if you have 3 stations, 4 stations, or 5 stations, how we can compute the average, or how we can draw these polygons. These are the polygons. These are the polygons. This is the polygon, and this is the polygon. So Thiessen Polygon Method. So these are the polygons. Something we have polygons, shapes of different form, and so on. So let us now continue. Assuming that now we have 3 stations. In the first case we had 2 stations. Now we have 3 stations. If we want to draw polygons, how can we proceed? Assume that we have an area given catchment. Let's say one catchment. Let's say Mukungwa catchment, one of the catchment in Rwanda. Assume that we have a catchment. We have a catchment called the Mukungwa catchment, and it has 3 stations. This is the whole catchment, Mukungwa catchment, and we have maybe 3 stations. One station maybe is in Muko, another station is in the town, another maybe in a remote area, and we want to draw the polygons, or we want to use this method, the Thiessen Polygon Method, to compute the average rainfall. So how can we proceed? First of all, we know we have to draw line joining all the stations. In this case, we have just to draw. This is just the first line. This is another line. And this is another line. So this is the line joining A and C. This is the line joining A and B. This is the line joining B and C. This is the first step. We are done with the first step. The next step, what do? We have to draw what bisectors. Bisectors, these are just lines which cut or which divide this line into 2 parts. So what do? Assume that the middle of this is maybe here, and the middle of this line is maybe here, and the middle of this line is here. So what do is just if you have a ruler, but here we try what to do. We try to do this. This may be this is the first bisector, and this is here. In this case, we have another bisector. Another bisector. We are trying, and here we have another bisector. Another bisector. So what do we do next? Once we are done these bisectors, these are bisectors. So we were saying that these are bisectors. I mean, bisectors. We have one bisector here, another one, another here. So these are what we call bisectors. Bisector, another bisector. So after what do we do once we have drawn our perpendicular bisector, which just cut our line into 2 equal portions? So which means this distance is equal to this distance is equal to this, and this distance is equal to this. We proceed, we extend these lines. This is the third step. We extend in both directions. This should be a straight line. We extend this as well, and we extend this as well until they meet. So you see that now my 3 bisectors have divided the whole catchment that we call the Mukungwa catchment, one of the catchment in Rwanda. The 3 bisectors have divided our catchment into 3 portion. So meaning that this is just an area which is represented by a station edge. So meaning that if we have maybe measured at A, assume that at A we have measured, let's say, 5 millimeters. At A we have 5 millimeters. At PA is equal to 5 millimeters. 5 millimeters. So meaning that all points in this portion, halfway to another station, should have equal rainfall depth, meaning we have 5 millimeters in all parts of this. So when we go to B, this is another weather station or rain gauge. Assume that this station has measured, let's say, 7 millimeters. What does it mean? This means that all points of this area receive the same rainfall, meaning that if we do this, so this area receives the same amount of rainfall, which is PB. In this case is 7 millimeters. So let's go to C. If we move to station C has an area which can be represented like this in blue. So assume that maybe the measured rainfall depth at this point, let's say maybe it is maybe 6 millimeters. 6 millimeters at C. PC is equal to 6 millimeters. These are different rainfall depths which have been measured across the basin or the catchment called the Mukongo catchment. So then what is next? Once we have plotted all the polygons, these are called the polygons. These are called 3 polygons. This is polygon 1. This is polygon 1, this is polygon 2, this is polygon 3. So meaning that if we use the Thiessen Polygon Method, Thiessen Polygon, the word polygon means this. This is polygon 1, polygon 2, polygon 3, polygon 1, polygon 2, polygon 3. So the next is to do what? To compute the representative area of each rain gauge. So if you have this is what we were saying in the first case, if you have maybe, let's say, if you have what we call planimeter. If you have this device, you can measure this area. Assume maybe the first area, assume that area H, which is this. Let's say that maybe it is maybe 100 meters squared. This area. Once we computed this area, assume that we have got 100 millimeters squared. Area A is equal to 100 meters squared. And the area 2, once you compute this area you get maybe, let's say, area B, let's say maybe 70 meters squared. Let's say maybe area B 70 meters squared. And the last area, this area C, let's call it maybe 80 meters squared. Area C is equal to 8 meters squared. Now we have precipitation recorded in each station, and we have corresponding areas. Area, this is the precipitation, this is the area of this catchment. I mean this portion. This is the precipitation and rainfall depth recorded in this area, and the area is equal, the size of this portion is equal to this, and this one is equal to this. So once you have everything, now the next is to compute the average rainfall in this catchment. So the average rainfall, we say that you take the product of area times the precipitation. Once you made the whole sum, we divide it by the total area. Meaning that in this case, this is the precipitation H times the area H plus precipitation B times area B plus precipitation C times area C. So once you are done, you sum up all the areas, meaning that we have area A, area B, area C. So if you want, you can replace and get the value. This is easy. So trying to replace every value, so we get this now. So if you want, you can compute the numerator. You get 1470 over, so this should be meter squared. So if you want, we have here 100 plus, this is 150, 250. Sorry, this is meter squared, which cancel each other, and we get 1470 divided by 250. We get average precipitation of 5.88 millimeter. So mainly the average precipitation in this catchment is equal to this. You see, we have considered the precipitation and the corresponding area it represents. The product, you sum up, you divide the whole area to get the average precipitation. This is how we can proceed if you have three rain gauges or 3 stations. So in this example now, we have like 5 stations. We have station A, B, C, D, E, or rain gauges. Assume that in this catchment we have 5 rain gauges, and each has measured a given rainfall depth. So how can we compute the average rainfall or the mean precipitation of the whole catchment? So remember we are still on Thiessen Polygon Method. So first we have seen that if you want to use this method, what do you do first? What do you compute first? If you want to use this method, first of all, you have just to draw lines joining all stations. Or neighboring, assume A. What are the neighboring stations of A? Is neighbored by D and B. So we have just lines. These are lines, straight lines. I don't have a ruler, I'm sorry for that. So this is another line, straight line, which joins A and D. So let's see, B is just neighbored by, the neighbor of B is A, C, E, D. So meaning that you have to put lines, this kind of lines. And C, we have to do this. And E, we have to do this. So D is neighbored by A, B, and C. So we have to do this straight line. E is neighbored by this. Something like this. So, meaning what? Now we have drawn lines joining all stations. What is next? Is to find out what? To draw bisectors. Bisectors, those lines which divide this line into 2 equal portions. Meaning what? And the bisector should be perpendicular to this line. Meaning what? I have to do this. And that here I do this, maybe something like this, which is perpendicular to this. And here I have to do something which is perpendicular here, like this. And here I have to remember this distance is equal to this, this is equal to this, this is equal to this, and so on. So here I have to draw something like this. and here I have to draw something like this, which is in the middle. So, and here I have to draw something like this. So mainly these are the beginning. This is the beginning of our bisectors. So what is next? So we have just the bisectors on each line. Bisectors here. So what is next? The next thing is now to extend these lines, which means if I extend this, it becomes like this, and if it comes in this way, I continue like this. And this one I have just draw it. Draw this. Continue like this. Draw this in this way. This I extend it in this way. I draw this in this way. This is extended in this way. Remember here there is also another bisector. So another bisector which was forgotten. So I can continue in this way. I can continue in this way. So something like this. Now we have the polygons. We have the polygons. If you see well, you see that we have like 5 polygons. So if you have a ruler, you can do it just perfectly. Me, I have tried my best in this way. So if you want, now you have 5 polygons. 1, 2, 3, 4, 5. We have 5 areas. Meaning what? Meaning that the precipitation which has been measured at A is the same in this point, in all points of this area. So the area, this is the area represented by station A. This is the area, let's call it maybe area 1 if you want. Precipitation which was measured here, let's call it precipitation 1. And here this is area 2, let's call it area 2. The precipitation which has been measured here, let's call it P2. The precipitation here is the same. The precipitation in this area is the same. This is represented by blue, is the same. Precipitation in all points here is the same. At C, the same thing. The same thing, let's say that the area measured here, let's call it A3, and the precipitation here is P3. And let's do this maybe. So this is the same area, meaning that all points which are in this area have received the same amount of rainfall depth. So if we continue in that way, let's do this. In D, let's do this. So this is another area in D. This is, let's call it maybe area, if you want to, let's call it area 4. The precipitation measured here, let's call it P3. And the D, which is the last, the E, which is the last, let's do this. Let's do this maybe. Let's do this. This is another area at E. So this is area 5. Area 5. And precipitation measured here, let's call it P. This is P. This was P1, P2, P3, this is P4. Let's call this P5. P5, area 5. So we are now done with just the drawings. What is next? If you want, you can now compute this area. We have said that if you want to measure these areas, what can you do? If you want to measure these areas, what can you do? You can use a planimeter. Planimeter or grids. Grids or just these small equal. So if you want, you can draw equal small, just rectangles, something like that, or just small cubes, something like that, or squares. The squares of known size you can easily plot and know the size of all this area. So if you want, you can use a planimeter whereby it just goes around the area in equation, then you know the area. So these are the area computed. So if you want to know the overall average precipitation, so average precipitation will be equal to what? Area 1 times precipitation 1, meaning this area, its size times precipitation measured at that station, times area 2 times precipitation 2. So the whole area, this whole area times the precipitation times the area, plus this area, area 3 times the precipitation which was measured at the station C, meaning A3 times the P3, plus what? Plus what? Plus area 4 times the P4, the fourth, which one? Plus area 5 times the P5. The whole divided by summation of areas. Then 4. In general, this is how we can compute the average precipitation when you have like five stations. Generally, that's how we compute. We draw the polygons. These are called the polygons. This is a polygon. 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 That's why the method is called Thiessen Polygon Method. We draw what we call polygons. Let's try using a numeric example to better understand. Good. So now here we have an example on Thiessen Polygon methods. Using Thiessen Polygon methods, find average rainfall over a catchment. The data is, so we have our data, we have just a rainfall gauge station, we have 5 rain gauge stations, A, B, C, D, and E. We have area measured by, or area enclosed by each polygon, and we have precipitation measured at each station. If you want to better understand, it's like the previous example we have done. We have in the same case we had also just we have like 5 stations. The same way we have 5 stations. If you do this, you do this, you do this, do this, you do this, you do this, you do this, something like that. You do this, something like that if you want. If you want to do this, maybe we have like we have something like this. We have like this. If you remember the way we computed everything, it was like this. So we have just each area. We have the first area. We have the second area, we have the third area, we have the fourth area, and we have the fifth area, something like this. And we have precipitation measured at each station. So we have it. How can we compute the average precipitation? Do you remember the formula we have presented? So immediately, if you want, you can do it in a tabular way. You can maybe say the area times precipitation. Area times precipitation. If you want to do that, so what can we do? So you can take, if you remember, the formula just says what it is just P average is just 1 over n summation of what? Precipitation times the area over the total area. If you want. No, this is not. This is this over the total area. This is the total area. If you want, this is mainly the formula how we use it. So Now the product, what will be the product? So let us compute the product here, and then we will be done with the exercise. So it is now clear. We have tried to compute everything. So first of all, what you do, you can just try to find out the product area times the precipitation in each column. So at station A, we have taken the area of that polygon times the precipitation measured at that station. If you do the multiplication of the product, you get this. On the station, multiply, you get this, and so on. Multiply, you get this. So remember, these are the unit of this: kilometer squared, millimeter. So this, everything is in this unit. So the average precipitation, now the summation, you remember the formula, you do the summation of precipitation times the area, the summation of this is the summation, this is the summation of all these things, which is this. And the summation of areas, you sum up all the areas, you get this. So the precipitation, average precipitation will be equal to 85.6 watt kilometer squared millimeter over what? Over the 196 kilometer squared. They cancel each other, and the precipitation will be obtained in what? In millimeter. So trying to take a 85.6 divided by 196, you get 31.05 millimeter. This is mainly the average precipitation in that catchment. That's how we can compute it.